Okay, YouTube, in this video we're going to look at the general process for solving what we call a logarithmic equation. So recall that a logarithmic equation is any equation containing a variable in the logarithmic expression. So all of these that you see here, these two equations here, would be examples of logarithmic equations in which we'd want to solve for some unknown value that happens to be on the inside of the logarithm. So our process for doing this is thus. We say using the definition of a logarithm to solve logarithmic equations involves, first of all, expressing the equation log base b of m equals c. So what we want to do here is basically indicate this. We want to isolate the log. Okay. And so you can see that on the left side here that it is isolated, but number 2 says using the definition of a logarithm, let's rewrite the equation into an exponential form. So excuse me, recall that our base here to the power of this c over here gives us m. In other words, if we were solving for m, we say what does m equal? I can tell you straight up that m equals b to the power of c. So in this case, if I'm solving for m, then I'm done. But if there is something more than that there besides just m, maybe an expression, we can solve for the unknown at that point and then check our solution by plugging it back into the original equation. So excuse me, let's take a look at these two examples here with our checkpoint 6. So we have log base 2 of x minus 4 equals 3, and checking our first step over here on the table, basically we want to isolate the log. And so what I mean by isolating this log is I don't have like a plus 3 on the outside that I need to subtract from both sides. I don't have something like 100 times the log base 2 of x minus 4 where I'd have to divide both sides by 100. All we have is the log. So since that's the case, what we're going to do is we're going to rewrite this expression. So when we rewrite into exponential form, what's going to result is something that might make a little bit more sense. We'd say, well, our base, 2 to the power of 3 equals this. In other words, 2 to the power of 3 equals x minus 4. And so I kind of like solving logarithmic equations just for this reason alone. You can just rewrite it. And, you know, solving this would just be as easy as adding 4 to both sides. So we would end up with 2 to the third plus 4 equals our value that we're looking for here, or that 8 plus 4, or 12, is equal to the x that we're looking for here. So in terms of checking this in the original equation, I do want to make sure that we make a habit of doing this. We say 12 minus 4 equals 3. We could see that log base 2 of 8 is 3. And if we want to be sure here, is this true? We'd say 2 to the third power equals 8. That's absolutely true. So taking a look at letter B here, what I wanted to do is make sure that we involve an example that has a natural log, or a log base e. Excuse me. So let's remember that this expression here, we don't write it this way, but it means the same thing as this. So when we rewrite this, first things first, let's go ahead and isolate the log by dividing both sides by 4. I'm going to bypass this particular entry here, and we're going to say then, dividing by 4, we have the ln of just 3x equaling 8 over 4, which is 2. So knowing that our base here is e, I can still kind of imagine that it's there. Then this expression, rewritten, we say rewrite, would look like this: e to the power of 2 equals 3x. So you can see how once you get to this rewrite, then really all it becomes is just isolate the unknown because it's no longer in the exponent. So we get 1/3 e to the second power, or e to the second power divided by 3. However you'd like to write it, we do need to find a decimal for this. So I'm going to go ahead and do that. I'm going to say, well, e to the power of, it's going to be behind our ln key, so e to the power of, whoops, second ln, and then we'd have 2. And what we need to do is take that and divide it by 3. That's the option I'm going to go with here. And we get about 2.46. So x is approximately 2.46, and we could certainly check this by plugging it back into the original equation. Cheers.